Hey guys, this video is going to cover a couple of the homework problems that I gave you last time, one from section 4.4 and another one from section 4.5. I didn't want to do any more than that because I was afraid the video might get a little bit too long. So what we're going to do first is look at number 48 from section 4.4. Okay, so here's our problem. A manufacturer of tennis rackets finds the total cost, C of X in dollars, of manufacturing X rackets per day is given by C of X is equal to 400 plus 4X plus 0.0001X squared. Each racket can be sold at the price of P dollars, where P is related to X by the demand equation. P is equal to 10 minus 0.0004X. If all rackets that are manufactured can be sold, find the daily level of production that will yield a maximum profit for the manufacturer. So we are maximizing profit, and X is going to be our independent variable. That's going to be the daily level of production that will give us that maximum profit. So what we want to do first is find P of X. Now I'm not given P of X, but I'm given all the pieces that I need to find it, okay? Remember that in a previous section we found out that the revenue is found by multiplying X times P, and P is given here as 10 minus 0.0004X. So what I do is I just distribute an X through that. That's going to give you 10X minus 0.0004X squared. And then we already know the cost. That's given in the equation. 400 plus 4X plus 0.0001X squared. So we put together our profit by saying profit is equal to revenue minus cost. So our profit is equal to 10X minus 0.0004X squared minus, we're going to subtract all of the cost function. So that's going to change your sign on every term. Got 2X squared terms, got 2X terms, and I have one constant. So let's clean that up just a little bit. Before we maximize, we've got to have it simplified. Otherwise, it's going to be a little bit trickier to deal with. I'm going to go ahead and pull that constant to the front. And you could rearrange this however you wanted to. But then you're going to have a 10X minus 4X, so plus 6X. And then if you add your 2X squared terms together, they're both negative, so they become 0.0005X squared. Okay? Now, to maximize profit, what we're going to have to do is take the first derivative, because we need to find our critical values. We haven't talked yet about what the limits on our X variable are going to be, but we will look at that in just a minute. So if I take the first derivative, I'll lose my constant term. I still have a 6, and then I'm going to have 0.001X. Okay, so a little linear equation. That makes it much easier to solve. We just simply set that equal to 0. I'm going to move the X term over since it's negative over there on the left-hand side. Then divide both sides by the 0.001, and you wind up with 6,000. Okay, so that's our critical value for the daily production. When we check to see what's a maximum in this particular instance, we need to see where our maximum point might be. We look at critical values. We also look at end points. Okay, so the 6,000 would be a critical value. Let's talk about what's happening at the ends of our possible values here. First of all, we know that we can't have an X value that's less than 0. I know that because we're talking about producing a certain number of things in a day. So you wouldn't have anything less than that. That would be like your smallest value you could possibly have. So that would be considered an endpoint. Even though I think by common sense we can tell that that's not going to yield our maximum profit. So we really don't even have to look at that as far as finding a value for it. The critical value is the 6,000 that we just calculated. That's the only critical value that we have in this particular instance. And as far as the other end of the spectrum, our largest value for x, we really don't have that defined anywhere. Obviously, there would have to be one. It couldn't go literally off to infinity, but there's no mention of where it might be. So we actually don't know another endpoint. Now, what that means for us is we really kind of need to analyze what's going on at the critical value a little farther than just looking to see which one has the highest y value. Now, it's likely with these problems that you've got, whatever value you do find for the critical value will be that maximum or minimum value that you're seeking, but it's not a bad idea to take a look at what's really going on. So one thing that we know, just by looking at the original equation right here, this is a quadratic equation. That means that it graphs as a parabola. Now, parabola is a cup-like shape, a cup that will either open up or down, and it actually is really easy to tell which direction it opens. If you will look at the sign that's on your x squared term, it's supposed to be your leading coefficient. This particular equation, the way I have it written, it's written in descending order instead of ascending. I'm sorry, I have that backwards. It's in ascending order instead of descending, so it's not literally the lead term, it's the last term. But it's the sign on the x squared term that tells you this. If it is negative, that tells you that the graph opens down. I forgot my N. Well, that looks bad, doesn't it? I'm sorry. Let me try that again. Opens down. So your parabola makes a frown like this. Well, what that tells us about, our endpoints and our critical value is that the critical value is going to be that top point, okay? We can also see that a little bit by using the second derivative test. You can work through it that way too. Let's go ahead and find our y value for this that goes with it to see our maximum profit, and then I'll talk about the second derivative test in relationship to this problem too. Now, you will notice in the wording of the problem itself, it doesn't actually ask you for that maximum profit, but a lot of the problems do. So let's go ahead and find that. The question that's asked in the problem asks for the daily production level, which is going to be the 6,000. Let me see how it puts it. Rackets per day, okay? So rackets per day. Okay, but we can find the profit level pretty easily by plugging the 6,000 in to our P of X. Negative 400 minus 6 times 6,000. I may have said that wrong a second ago, but 6 times 6,000 is going to give us 36,000. We can go ahead and write that down. And then we're also going to have, and that's going to be plus, I'm sorry. We're also going to have 0.0005 times 6,000 squared. And if you work that out on the calculator, that profit is 17,600. Now that's per day. Okay, that's your profit level per day for this particular problem. And you could look at it from the endpoint there at 0 as well if you wanted to, but like I said, common sense already kind of tells you that's not going to work out. And then if you plug in 0 for your x value into your profit function, you wind up with negative $400, which clearly is not going to be your maximum profit. Okay, so you can kind of see there already that that endpoint's invalid regardless. So we don't have another endpoint on the other side, we don't have anything else to check. As I mentioned, we actually already see that that is our maximum because we can tell that from the parabola here. In the little analyzation that I did, we know it's going to be a parabola because it's quadratic. Since that leading term, the x squared term, is negative, it tells us it opens down. So whatever we find for the critical value will be the absolute maximum of this particular problem. But you can also check the second derivative. If we do that, the second derivative test will wind up giving you just a constant, a negative 0.001. You can go back and look up at the first derivative and confirm that that is in fact the second derivative. Second derivative will always be negative. So your critical value is a maximum, because negative second derivative means that you're concave down, which is what we see when we look at that parabola shape that I drew earlier. That's concave down. So we can see from either position here that this is our maximum, or rather it's the value that will yield our maximum profit. Okay, so I guess a better way to put that would be maximum profit at an X value of 6,000 rackets per day. Okay, so that gives you a look into another problem from 4.4. Now let's look at one from 4.5. The one I've selected for this particular problem is number 8. And here's the wording of number 8. If an open box has a square base and a volume of 108 inches cubed and is constructed from a tin sheet, find the dimensions of the box, assuming that a minimum amount of material is used in its construction. So when it says assuming that a minimum amount of material is used in its construction, it's asking you to minimize surface area. Now we're just talking about a rectangular shaped box, so the volume and the surface area for this particular geometric figure is not that complicated. Volume is going to be equal to the length times the width times the height, or whatever order you want to use for that particular thing. We are told that it has a square base. Okay, we're not told the size of that square base, but we're told that the base is a square. And so what I'm going to do is let W represent those sides. Okay, the length and the width are going to be the same. Okay, we'll let the length and the width be the base. And then the sides, of course, are going to be folded up from squares or rectangles, one on each side of that base. Okay, so the only dimension that we don't know from the sides is the height of the box, which will be the other dimension of each one of those little rectangles there. Okay, so that simplifies the problem a little bit. Now instead of having three variables, we only have the two, the width and the height. We are also told that volume is equal to 108. So if L and W are both the same value, that can be written as W squared, and H is what we're looking for. Okay, so I can solve this for H. That will give me an expression that I can use to reduce my surface area equation here in just a second down to a single variable. Typically with optimization problems, you have a primary and a secondary equation. The primary is the one that you wind up minimizing or maximizing. The secondary is the one we just saw, which its function is to allow you to take the primary and write it in terms of one variable, because that's the only way we know how to take derivatives at this point. Okay, it's in one variable. Well, we can do implicit, but for optimization problems, we need it to just be in the one variable. So now what I can do is fix my surface area equation and use that so that all of my variables within the surface area equation are W's. Okay, so let me scoot up. Whoops, hit the wrong thing. You scoot up just a bit. And surface area is just all of those rectangles added together. So you have one base, which the area of the base is going to be W squared. And then that's going to be added to 4 times the side, because the side's going to be the same for all 4 sides. It's width times height. And we can replace that height with the 108 over W squared. And then we can simplify that. Whoops. I just noticed I goofed up right here. That's supposed to be a plus. So W squared plus 4 times 108 over just a W. Okay, then we can multiply the 4 times the 108. That gives me 432. don't know why I keep writing an equal sign instead of a plus. I'm sorry. Don't know where I'm getting that from. And I'll go ahead and bring this up so that we can take the derivative fairly easily. Now, a little bit later on, we may want to go ahead and simplify that just so we can kind of see what's going on the ends of the graph. This problem itself does not have closed endpoints. We know just because of the boundaries that we have for physical objects that our width can't be less than 0, but we don't have a maximum to this. We don't have an endpoint. And really, 0 is not a closed endpoint because we know that it's impossible for the width to actually be 0. So all we know to adhere to here as far as the domain is concerned is W has to be bigger than 0. So as far as the endpoints are concerned, we don't have any. So we'll have to analyze this a little bit differently. All right, to get our critical values, we take the first derivative of the surface area, which is going to give me 2W minus 432, W to the negative 2. And this is not a super simple equation to deal with. I can rewrite this so that I have a fraction we pull the W to the negative 2 down underneath the 432, and then what we do is we get a common denominator of W squared and then write it as one fraction like that. Then what we can do, find critical values, we set the numerator and denominator equal to 0. Well, the denominator equal to 0 is going to be a point that's not in the domain, because if you remember from back up here, when we first subbed all that out, right here, W's in the denominator, and so if we plug 0 in for W, we got a problem. It's going to be undefined, so I can't actually use that as a maximum point, so we don't even really have to analyze it here. We know it's not going to be optimized. Plus, from the domain situated from the problem itself, we know that W cannot be 0, so we don't have to really look at that one. I can work a little bit with the numerator. It turns out that if I factor out a 2, then what's left of the numerator there, the W cubed minus 216, is the difference of 2 cubes. That can be factored with a formula. It's something you learn in algebra, but you kind of have a tendency to forget it because we don't use it very often. 216 is 6 cubed. I'm going to write that right above there, so we've got that. There's a formula, like I said, and the first part of the formula to get the factors is you just take the cube root and the same sign and the cube root and make a little binomial factor. And then the other factor will be trinomial, and it's the square of the first cube root. It's the opposite sign, the product of the 2 cube roots plus the square of the last cube root. So that's how we can break down the numerator. And if you take that and set it equal to 0, it turns out that the W minus 6 is the only one that actually gives you anything, because if you set this equal to 0 and try to solve it by the quadratic formula, the solutions are imaginary. So we can't use them. Okay, we don't deal in imaginary numbers in calculus, so we can't use those. This is our critical value right there. So we can kind of get some sense of what's going on at that particular critical value. We can do the second derivative test. Second derivative is going to yield U2 plus 864 x to the negative 3. And so if we plug a positive number into that, I'm not going to actually get the value because it would be 864 divided by 6 cubed, and then you add 2 to it, but you can tell that it's going to be a positive number. Okay, so this is going to be positive when x is equal to 6, so that means we are concave up. And I'm sorry, not x. Sorry, I jumped variables. You'll have to forgive me. When I worked this the first time, I used x instead of w, so I'm messing up here. So sorry about that. Okay. Concave up, and you'll have a minimum at W is equal to 6. And you can kind of get some idea that you could graph the original function. You can, analyze what's going on as the graph goes off to the left and to the right. There's going to be an asymptote at 0, but you also know that the graph can't go with any W values that are less than 0, so you don't have to worry about what happens on the other side of that asymptote. Alright, so that is it. That's how we do this particular problem. Now I think let's scoot back up and see what it actually asked us to find. We want to find the dimensions of the box, so what we found here is W. So the width, and therefore also the length, what we're calling it, is 6. That makes up the square base. And then our height was 108 divided by the width squared, I believe. And that gives us a value of 3. And let me scoot back up and see what our inches. Okay. So 6 inches on the width and the length, and then 3 inches on the height. And that's our answer.